Dear students, today we are going to talk about chemical kinetics. Chemical kinetics states that how fast a chemical reaction takes place. To take place a chemical reaction, molecules must collide with the correct orientation and with enough energy to cause bond breakage and formation. Therefore, let's consider the collision with correct orientation and the activation energy as the key factors effect on the chemical reaction. Consider a system which randomly moving gas molecules in a container. Let's talk one time frame in this kind of system, and then we can calculate the kinetic energy of this system. Then we can derive the molecular kinetic theory equation as shown in the above equation. However, we are not going to talk about more in the chemical kinetic theory. However, let's consider only the factors effect on the chemical reaction rate. Randomly moving molecules as shown in previous example are colloid each other. As shown in this example, the colored circles are representing individual atoms. Think about this kind of Ron orientation. These green color circles colloid with blue color circles are not react each other. Therefore, the repelling these molecules. Therefore, no reaction take place in this wrong orientation. However, if you rotate this molecule into take a proper orientation, this example, therefore, this green color circle meet another green color circle. Therefore, this is the correct orientation and the reaction is taking place due to the correct orientation. The next requirement is activation energy. Consider the energy gain from this ball to cross the barrier. Apply F1 force is not sufficient to cross the barrier. Therefore, when you apply F2 force, which is higher than F1, the energy requirement is enough to cross the barrier. The minimum energy requirement to take place a chemical reaction to overcome the activation barrier we call activation energy. This is an example shows the diagram which represent the energy in y-axis and the reaction pathway in x-axis. This example is the reaction which participate only single molecule, or we call unimolecular reaction. In here, the rearrangement of methyl isonitride to acetonitrile. Rate of a reaction is concentration change of a reactant or product with the time. Let's take this example. Hydrogen and iodine react to form hydrogen iodide. With the time, hydrogen and iodine concentration will decrease. Let's take one point and we can calculate the hydrogen concentration change with the time, or iodine concentration decrease with the time. This represents the rate of this reaction. Or we can consider the increment of hydrogen iodide. This is the increment of product of this reaction. Then let's move to the factors that influence the rate of a reaction. Let's consider a reaction, metal react with acid. Here the example is nickel metal react with sulfuric acid to form nickel sulfate and hydrogen gas. The time taken to totally dissolve this nickel metal in the sulfuric acid solution is called the reaction time. Let's draw a graph. In y-axis, the total amount of hydrogen production with the time. Let's first consider the physical state of nickel metal effect on the reaction rate. Here, the small pieces of nickel metal dissolve in sulfuric acid. The graph you can obtain like this. Therefore, the reaction time taken around 1 minute, let's assume. Then, if you use this kind of large pieces, graph will change into this kind of graph. Then the time taken to totally react will more. Therefore, we have around 2 minutes. Then, if you use this kind of powder, same amount, same mass, however, the reaction get faster than the previous reactions. Next factor effect on the rate of the reaction is concentration. Let's take the sulfuric acid concentration effect on the rate of the reaction. If you use concentrated sulfuric acid to this reaction, the graph will obtain like this. The time taken 1 minute. If you use diluted sulfuric acid, the graph will change according to this kind of graph, and it will take more time to react total nickel metal in this sulfuric acid. This is the rate law we call the concentration effect on the rate. Let's discuss this rate law later. Next factor effect on the rate of the reaction is temperature. If you use a low temperature to react, the reaction is slower than if you use in high temperature. Therefore, time taken at the low temperature T1 and time taken at the high temperature is T2. Therefore, T1 is higher than T2. If you increase the temperature, the reaction will take place faster. This equation is called Arrhenius equation, and it's represent the temperature depend on the rate. We can discuss this later. Next factor effect on the rate of the reaction is catalyst. Catalyst increase the rate of a reaction by decreasing the activation energy of the reaction. Therefore, obviously catalyst change the mechanism. Let's consider the example of hydrogen peroxide to form water and oxygen. This is the uncatalyzed reaction. If you use bromide ion into hydrogen peroxide in acidic medium, the hydrogen peroxide will react with bromide ion to form water and bromine. This is some kind of oxidation of bromine and the reduction of hydrogen peroxide into water. Then this bromine again react with hydrogen peroxide and to form oxygen and bromide ions with H plus ion. Therefore, when we consider here this H plus, we can cancel out, and 2 bromide here, 2 bromide and bromine, and here bromine. Therefore, then let's consider this reaction is similar to the previous reaction. Therefore, when we add bromide ion, it acts as a catalyst to form the similar product of the reaction with compared to the previous reaction. But here the reaction rate is higher and the reaction take place faster with compared to the previous reaction. Therefore, if you add catalyst, the reaction mechanism change and the reaction take place faster. Let's consider the different type of catalyst. First, the heterogeneous catalyst. Here, the ethene react with hydrogen to form ethane in the nickel catalyst. Nickel is solid and other reactants or products are gases. Here, hydrogen and ethene gases are absorbed into the surface of catalyst. Then bonds are breaking and making new bonds and then leave the products from the catalyst surface we call desorption. Therefore, these kind of steps are involved in heterogeneous catalyst. Next type is homogeneous catalyst. This is the example. Alcohol react with carboxylic acid to form esters. And also the example we discussed in the previous slide also a homogeneous catalyst. Here all reactants, products and the catalyst are in same form in liquid state. Next type of catalyst are biocatalyst. In here enzymes and there are several proteins are involved in catalyst. Here the example of enzymes used as a catalyst to break down another molecules. Next factor, effect on the rate of the reaction. We can say any form of energy. Example, light or any radiation. The example we took in the previous slide, hydrogen peroxide convert into water and oxygen will faster if you keep the hydrogen peroxide in sunlight. Therefore, we can increase the rate of the reaction using any other way of radiation or energy form. Another example, chlorine and hydrogen convert into HCl will increase the rate with the form of radiation applied. Summary up to now, the rate of the reaction depends on the physical state of the reactants or the concentration of the reactants and the temperature and the catalyst and other energy sources given to the reaction. Let's move to the basic concepts and terminology in reaction kinetics. Rate of a reaction is the concentration change with the time. As we learned in previous slides, here we can write down the rate of the reaction in different ways. This is a common reaction, A plus B converted to C plus D. Here we can write down the rate of this reaction as the concentration D A concentration into dt, D B concentration into dt and D C concentration into dt or D concentration into dt. So we can get the relationship between these rates using the stoichiometric numbers. This is the reaction rate, the relationship between each form of reaction rate. Therefore, as we know in our previous example, we can write down the reaction rate as this kind of ways. Therefore, the common way of writing down the reaction rate is this. Rate constant is a constant which quantifies the rate or the direction of a chemical reaction. The Arrhenius equation has the relationship between the rate constant and the temperature. Here in this Arrhenius equation, capital A represents the Arrhenius constant and EA represents the activation energy and R as usual the universal gas constant. Here we can write down another ways of Arrhenius equation to form the linear relationship. Therefore, log value of rate constant is linearly depend on the 1 over T. T is the temperature. When you are learning chemical kinetics, we should know different types of reactions. First, we can learn elementary reactions. A reaction that occurs in a single step we call an elementary reaction. The molecularity of a reaction represents how many reactant molecules are involved in the elementary reaction. This is an example of elementary reaction which involve a single molecule. We call, therefore, in this elementary reaction, the molecularity is 1. This is another example which has 2 molecularity because it contains 2 molecules in this elementary reaction. Next type of reactions are complex reactions. In the complex reactions, reaction take place through different steps. In these examples, you have 4 steps to final products. Therefore, complex reactions have several steps to complete. This kind of complex reactions have a rate determining step. Let's consider one example to show what is rate determining step. Think about this kind of bricks you have. There are 3 people moving these stones into this place. So therefore, think about these people are passing this stone from here, and the second person pass this stone to third person, and third person fill into this place. In this process, think about the first person will take 3 stones per 1 minute, but the second person can take only 2 stones per minute, and 4 stones per minute can move from third person. But you know how fast this place will fill. It is definitely 2 stones per minute, because the second person is the key factor of this process, because he is the slowest person. Therefore, the rate determining step is the second person. Therefore, in this kind of reactions also have the same rate determining step. In this example, 2A plus B convert into A to B using 2 steps. One step AB forming by reacting with A plus B, and then this AB react with another A and to form A to B. Here the slowest step is we call the rate determining step, because this reaction rate depends on the slowest step. Rate law is the most important equation when you are studying chemical kinetics. Take this example, this common equation as we learned in previous slides. These are the rates we can write down to represent the rate of this reaction. This is the rate law, the equation we can use to represent the rate law. Here, one side we have rate, then K is the rate constant, and A represent the concentration of A, and B under the bracket we represent the rate concentration of B. And the P and Q letters are represent the order with respect to the particular molecules. Here the P represent the order with respect to A and Q represent the order with respect to B, and the total order or overall order represented by P plus Q. What is this order? Actually, the order represents how many molecules of A or B of any reactant involved at the rate determining step. If you consider an elementary reaction, we can write down the same rate law for this kind of elementary reaction. As you know, an elementary reaction contains only one step. Therefore, that is the rate determining step. Therefore, number of A molecules in here represented by the stoichiometric number simple A, and the number of B molecules represented by their stoichiometric number simple B. Therefore, when you write down the rate law, the P we can substitute to A because the order with respect to A is A number of molecules, and Q represent the B number of molecules in this reaction. This table represents the molecularity and the example of elementary reactions and the related rate law. Therefore, you can understand how you can write down the rate law according to the reaction. Now consider another reaction which is not an elementary reaction. This kind of reaction we can't apply this stoichiometric number as the order with respect to their molecules, because these kind of complex reactions have different steps. They may have two or more steps. Therefore, the rate determining step is the slowest step of this reaction. Therefore, the P and Q is equal to the stoichiometric number of that slowest step of the reaction. Therefore, we can't apply the stoichiometry of the reaction for order with respect to their reactants or the overall order. Now let's consider different ordered reactions. Zeroth order reaction that represent any of molecule or the concentration is not depend on the rate of this reaction, because the slowest step, the stoichiometric number is 0 for reactants. Therefore, in the slowest step, they are involved only the intermediate products. Therefore, you can write down the rate law of zeroth order reaction like this. In this kind of rate law, you can use to calculate the concentration at time t. Think about when you start the reaction at time 0 and now think about the time is t. Then we can write down this rate law by taking this into right side, and then you can write down this equation in the simple form. Then we can integrate this equation from time 0 to t. At the 0 time, let's think the initial concentration is A naught. Now the concentration is A. Therefore, when you integrate this equation, you can obtain the answer like this. Therefore, you can calculate the concentration at any time is equal to minus kT plus the initial concentration. Then let's consider half-life time, T half. What is this T half? It is actually the time taken to reduce the initial concentration into half. Now at the T half, the concentration change into A naught divided by 2. Therefore, using the previous example, using this equation, you can calculate the half time by apply at the time T naught, at the time T, now time is T half, and A is equal to A naught over 2. Therefore, you can simplify this equation and you can take the half-life as A naught divided by K. This is you can apply for zeroth order reaction. And first order reaction, the order of the reaction is 1. Therefore, you can do the similar way and you can take the relationship between time and the concentration by integration the similar equation, and you can obtain this equation. Therefore, ln A is linearly related to the time, and you can calculate the T half also using this equation. Therefore, in the T half, there are no terms in A. Therefore, whatever the initial concentration, T half is ln 2 over K. Therefore, the first order reaction, there's no depend on the T half, not depend on the concentration. Therefore, you can use these two equations to identify first order reactions. For second order reactions, also you can do similar equation you can obtain. Please practice this kind of mathematical calculations to take second order reactions. In this summary table shows equation related to different type of order reactions. Therefore, you can use this equation to identify the order of the reaction. Let's move to the method to determine rate law. As you learned in the previous slides, zeroth order reaction shows the relationship with the concentration and the time in linear way. And the first order reaction shows the linear relationship between the log value of concentration of A with the time. And second order reaction, which shows the linear relationship between 1 over A to the time. Therefore, according to the shape of your graph of concentration or log concentration or 1 over concentration with the time, you can assume what is the order of the reaction. Next method to find out the order of the reaction is the initial rate method. As shown in this example, if you can find out the initial concentration of one reactant and other reactant, or the rate of the reactant, so then you know this one and you know this and this point. Therefore, unknown, you have only 3 unknown parameters. Therefore, you can write down 3 equations by applying these 3 data set. Then you can calculate unknown terms using applying this data into this equation. Please practice this method because you will have to answer this kind of question in your exam. Next method is half-life method. Now you know what is the half-life of first order reaction, zeroth order reaction or second order reaction. Therefore, if you write down time and the concentration for the half-life, you can definitely obtain the pattern and then you can assume what is the order of the reaction. That is the end of this presentation. Please find out other sources also to learn chemical kinetics, and then you have to answer for the exams. Thank you very much for listening.